Before we get into circuits, let's finish talking about electrical power. As electrons travel through circuits, they do work. As they do this, they generate heat through friction, which is simply a type of energy. Energy and work, we know, is measured in joules. Recall that power is the rate of energy use. Rate, as soon as you see that word, you should think time, so the amount of energy per time. This is what an electric bill looks like, or an energy bill per se. We've already talked about energy and we actually did the problem, the energy, how much power you use in your rooms and how much it costs to operate your rooms. So we've already talked about this a little bit. Here on Long Island, we use PSE&G. If you've seen electric bills come to your house, it has a orange symbol on it. You've all seen it before. You can ask your parents, guardians, grandparents, who's ever at home to check out their electric bill, and it should look just like this if you haven't seen one already. The power built up in a circuit depends on how much energy each electron has. That's what we call voltage, electrical potential energy. The more voltage means that we push electrons harder, which is going to yield more power. They have a direct relationship. It also depends on how many electrons are flowing through it, and that we call current. The more current means more electrons are produced through friction, which yields more power. Again, a direct relationship. Here's the power law. P equals IV. Power in watts is equal to current in amperes multiplied by voltage measured in volts. Power, again, we know is measured in watts. That doesn't change. What is the power generated in a circuit that conducts 10 amps of current when connected to a 15-volt battery? Well, they're asking us for P, they're asking us for power. They tell us that we have 10 amps, that's our I. 15 volts is our battery, is our V, our voltage. Using the power law, P equals IV, we end up with 10 amps multiplied by 15 volts to give us 150 watts. How much current is drawn or how much current is used by a 100-watt light bulb when it is connected to a 120-volt power supply? They give us PR power, 100 watts. They tell us 120 volts. We're looking for I. P equals IV. 100 watts divided by 120 volts gives us 0.83 amperes. We're able to create a couple of other equations just by using Ohm's law, V equals IR, and P equals IV, our power law. We can take these and we can substitute into each formula to create new ones. So first, we're able to substitute out our I, and we end up with P equals V squared divided by R. All we did was replace the current, the I, with I equals V over R. We're also able to do this by substituting in V, and by doing that, we get I squared times R. We already know the formula P equals W over T, work divided by time, or energy use divided by time. So we have all of these equations here. Each one is on your reference table, page 4 in your reference table. What is the power generated in a circuit with a resistance of 300 ohms if it conducts 2 amps of current? We're looking for power, we're looking for P. 300 ohms is our R. 2 amps is I. Using the formula P equals I squared times R, only the I is squared, so we end up with 2 amps squared multiplied by 300 ohms gives us 1200 watts. You could also, if you're using scientific notation, you would end up with 1.2 times 10 to the third watts, or you can convert it to kilowatts. If you left it as 1200 watts, that is totally fine.